Okay, so
let's rewind and start all that again.
Let's rewind and start again. All right, so let me tell everybody. Hello, everybody. I forgot to start the stream. It's a 2, 3, 4-step process for some reason. And now we're live. I apologize. That's entirely on the old man here. Hello, everybody. We've been talking for 6 minutes, so we'll start again.
Yeah. All good.
Yeah, here's what it is. I had a camera failure. I had to move stuff around, and now the Go Live button is behind the other camera, so I did not see it in my field of vision. That's my excuse. I'm sticking to it.
Yeah, but it's definitely streaming now. Definitely streaming.
Definitely streaming. So let's go back, and I'll ask you. You had a good holiday. We're here back. I've had hardware failures just in 2 weeks. Stuff starts breaking just from sitting idle. But we are back.
2 weeks goes by, and I was just saying before we actually got the YouTube stream going, and it feels like it has not been 2 weeks since we last chatted, but a lot of stuff has been going on. There is so much to talk about today.
Right.
And yes, I did have a wonderful Easter, and for anyone else online who does Easter, I hope you had a great Easter as well. I got this shirt from a musical production with lots of, you can see sort of Metallica style logo. We had really cool musical production of Easter with rock music. It was fun. So I got the shirt for it. So Bill, you're showing us a DPO there. And what I was saying before, it looks like you're measuring something on the 128.
Right.
And we're looking at your screen, but you're remotely controlling that, right? So the scope's there, I can see it behind you in the background in the lab, but you're controlling it. Is it on Ethernet or are you on USB?
Yes, it is on Ethernet. Let me see if I can. The only thing is I have to wear glasses to see the controls. But for example, I can change the spectral, the type of DPO phosphor that we're seeing here with just by punching buttons on a web browser, basically.
That is so cool. So give us a quick background on what before we had digital phosphoscopes, right? We had storage oscilloscopes that were also called phosphoscopes in the analog days. And I remember
they had a grid that you wrote to the control grid. You imparted a charge to the control grid, and then it would change voltages, and then the electron beam could only go through the parts of the control grid that had previously been hit by electrons. And it sucked. I mean, I would use these things for everything it was worth. They were good for troubleshooting one-time events like a reset circuit, but to catch the kind of glitch that I was looking for in the setup today, you would never see it on a Tech 466 storage scope. It just wouldn't work.
Yeah, so I recall using them because basically they used a phosphor on the screen that had a long persistence of vision. So it was a cathode ray tube just like normal oscilloscopes, but the phosphor would stay lit up for a longer delay after the beam had passed it. So the idea, my understanding was, if you had repetitive waveforms, like if you're looking
they would get brighter and brighter as it pounded the same area over and over again.
Right, so if you send the same clock signal down a PCB trace and you're measuring the other end of the trace to see if it's got good or bad signal integrity, if you wanted to look at any ringing problems or reflections, if you send a repetitive signal, you get a repetitive result. So you can see where the waveform goes most frequently because the phosphor would be brighter in those places. So the DPO does that, but it does it using software to display it on the screen. And actually, it's given us a lot more because if you do spectral on yours, or temperature gradient, you can actually color code.
Yeah.
So what are we actually looking at there? You've got two probes on the board,
right?
And we're looking at the waveforms.
And you mentioned it's digital, and what's funny is while I was setting this up, my hand went to look for the focus control, and of course there's no focus controls on digital scopes, right? So I'm like, well, that's a little fuzzy. Where's my focus control on there?
Right, but it's meant to be fuzzy, right? Because it's
It's actually, yeah, it was meant to be fuzzy. It's just it's persistence, as you were talking about. So years ago, and up on the top, I thought you'd get a kick out of this, Ben. As you know, there's a wire on the board. I'm going to go over and point to it, but I'm not on my wireless mic. But Ben, what I did was, rather than run the jumper straight from one location to the other, and the jumper is there because there was a reflection, I ran it down to ground, and I made it into basically a transmission line. So hold on. You could see the wire right here.
Oh,
it comes
yeah.
down to the ground, follows the ground up to where it's going, so that it had a controlled impedance.
Microstrip.
Yeah.
Good. Yeah. You made a circular microstrip. Yep.
And I did that without knowing that that's what they were called back then. I just knew that I wanted, whereas the trace that had the problem with the reflection must have been making too many corners and was the wrong length and the wrong changes of impedance. I gave it a second path that had a better impedance. What would you estimate that is? I'd estimate that at about 100 to 120 ohms, a piece of wire on a ground like that.
We could actually calculate it.
We could actually measure that.
Why don't we do that? Because do you know the diameter of the wire?
Call it a 20 gauge wire.
So we could look up the diameter of that and the measure with a caliper, the diameter of the dielectric. We'd have to make an assumption that dielectric is PVC. So we'd look up the epsilon R of PVC and then open up Cook's Transcalc or AppCAD or one of those free impedance calculators that has actually the latest version of the Saturn PCB toolkit was just released too.
I saw that. 2 weeks.
So that's something else. I don't know if you've downloaded it.
And what is the Saturn PCB kit?
So Saturn is a company that it's a manufacturer. They're a contract manufacturer. They mainly fabricate boards. I think they're on the East Coast somewhere. They make boards and they do assembly for people. But they have this, and they've had it for many, many years now. It's one of the most popular tools. It's all the different calculators you might ever want for PCB design in one software tool.
Okay.
Let me see if I can...
So Sierra called me, PCBWay, and we'll talk about them, reached out to me, speaking of PC board manufacturers. But Sierra also called me in the last 2 weeks, and they were reminding me that they have quick turn PC boards also. So if you meet a certain criteria, you can do it online. But it sounds to me like any time the criteria is broken even a little bit, then you're back to submitting Gerbers and waiting for somebody to call you. But they're trying to move on, you know?
Yeah, they also, my understanding is they also have a bunch of calculators on their website too, which you can use for free, which are... Well, of course, that's one of their lead generators. And same with Saturn PCB. If you want to download it, you're going to exchange your email address. But I've never received any spam ever from Saturn, so they're pretty generous with it.
On Sierra,
I know I downloaded it, so I'm just going to try and install it real quick here because I haven't done that yet. But
what I was going to say is on Sierra, they've got a good design for manufacturing guide and then a design for manufacturing check, I think, on their website. Which tells you it's like, hey, you've got too big a hole, not enough annular ring, things like that. That will tell you about the reliability of your PCB in production. So, kudos to Sierra. They're one of the people I like for DFM, Design for Manufacturing.
Yep.
So, while you're doing that, go ahead.
I've done 2 factory tours with them. When I was in the Bay Area. So if anyone's ever in the Bay Area and you want to see the inside of a PCB factory, you call them and they'll give you a tour because it's probably the best way to really learn how you're going to deal with DFM issues is to understand in depth the process.
It's a lot of steps in there.
There really are. So I have, I don't know if I can share this with you real quick. I don't have the latest version. Let's see if I'm doing the right screen. Desktop, window, Saturn.
Your audio noise just cut way up.
Oh, someone started printing, and the printer's over there.
Okay.
It's noisy.
Okay. Well, as long as we know what it is.
I don't know if you can see this.
All right, let me look for your screen. Did you do a screen share?
I was sharing the app. Let's see. Let me try again. No, I'm sharing the Saturn PCB app.
So stop sharing and start sharing again. See if that fixes it.
Let's go with. Is that the right one? No, this one. So we're looking at the Skype within the Skype, but I'll bring up Saturn.
Whoops. That's not your. Oh, that's okay. Let me make that bigger.
Yeah, this is not. This is not the. So I was trying to just share the app, but the app won't go full screen.
Yeah, we're good.
A fixed size, but this is not the latest version. They just released version 8.4 or something.
Actually, we're not good. We're making an infinity tunnel just very slowly. But I can see the app.
Yeah. So this is just what it looks like. It's got all these different calculators for noise, crosstalk, coupling, impedance, and the conductor impedance. This one shows microstrip. This microstrip embedded, strip line, asymmetric strip line, dual strip line, and coplanar waveguide. They don't have the circular one in here, so maybe we would use AppCAD or one of the others for that. I'm going to stop sharing though, because
because the world may end if it keeps going too far.
Yeah, you can minimize me though for a sec.
Yeah, I'm trying. It's just fighting me. Ah, there we go. And we'll set that off to the side for next time.
So anyway, we could do that in theory.
Right. So we were talking about the old C128, and so we had a layout issue that caused a reflection at a bad time. Now, on what we're seeing here on the screen is on the bottom, the blue is RAS, row address strobe for the DRAMs, and it is holy. It is a signal that we shall not mess with, and we shall abide by the setup and the hold time, always and ever. Even on a read cycle, if you twitter the address lines right before the row address strobe, you can corrupt data. And people go, why? It's a read. No. And I had to have a DRAM designer tell me this. He said, internally, we're decoding the rows. And if you're moving them around, we got different rows coming online, and they can collide. So you don't want stability as your friend. Moving around the address lines too close to the row address strobe is bad.
You must. So the bottom line is the data sheet says there is a setup and a hold time.
Right.
A setup and a hold time before you're allowed to have valid data or valid address, and you must observe that minimum hold time. Yeah.
Right. And in addition to that, it means that you don't just ruin the cycle that if you violate it, you don't just ruin the cycle you're on. You could corrupt DRAM anywhere in the DRAM.
Yep.
Right? You can't predict what you'll do.
This applies today, not just with DRAMs from the 80s.
No, it's DDR3. All that stuff still does the same thing.
All DRAMs operate on the same principles on the inside. They're just doing it a lot faster. And they're using both edges of the clock, which is where the dual data rate comes from. Yeah, to speak about that real quick, if you think about a clock and we're clocking data right at the rising edge of a clock, a dual data rate is where we also clock on the falling edge of the clock. So we get twice as many data out of it, twice as much data. So here is this on the screen. If this is row address strobe, and here's our address line setting up. They're way out here. They're about 100 nanoseconds. And you think, well, there's tons of time, and there is. This is running in 6502 mode. And I'm seeing a lot of crinkly wrinkles on that, but they don't matter because it's all
way before.
So explain
that's actually my scope ground doing that probably.
Or is it? Or is it just
Well,
by
I
virtue of
won't
the
know
fact
unless I go making a good ground and doing all kinds of things that I don't want to do to a 35-year-old, Commodore thing, then ruin it.
right, but I'm just making the point too that signal integrity, we back in those days, and in simpler designs even today, if you're not going super fast, we could get away with it, right? We could have all that
Right.
ringing. We could have all that ringing because it all happened well before the setup time and the edge of the next transition, which is what we're looking
Right.
at there on your scope, right?
Right, right. So even if it wasn't just all my ground, what you're saying is true. It had time to figure it out ahead of time. And as a matter of fact, this little curve here, sometimes this is no address and this is the actual pull-ups. Sometimes this is the processor driving this. So,
Okay,
but
so
yes,
the different
there's some,
chips, right?
but it's quiet by the time Raz falls, which was your point.
Yeah. And so if we're dealing with however many, microseconds, or it's probably in the hundreds of nanoseconds of access time, 100 nanoseconds or 150 nanoseconds. What would you say, Bill? I don't remember from those.
It's
The
the setup time is probably about 10 nanoseconds, and we aren't all the way through the address buffer, so I need about 40 nanoseconds of cleanliness, and that's about what I have here. And honestly, those little bounces there, we called that good back in the 80s. I would have had to go in. Let's talk about scope grounds for a second. I have a big old wire going to ground right now because it was the best I could do and still make this shot count, right?
Yep.
In the old day, that's no good at real high frequencies. That's an inductor. Inductors resist a change of current, all these things that make it into a nasty open loop. I'll bet I could get rid of half that ringing and noise artifact by changing my ground, and the other half is probably just the 1980s speaking to us.
Yeah, yeah,
So
you're right.
now,
so someone
we
shared
have about
that.
100, yeah, so we've got about 40 nanoseconds here of cleanliness. I'm not going to go in and change the scale because I might break the setup up I'm about to show. But the problem was, it was when the Z80 kicked on that we saw an issue. So I'm going to turn on the Z80.
Okay. So again, what's that process? The 6502 goes into a halt mode,
Yes.
and the Z80 essentially boots up, but the memory's still full of whatever was in the memory before.
Ah, there we go. There it was. See that little trace right around here?
Yeah, yeah.
Okay.
It's just a
now
ghost.
I still have my
Happens
40
just every
because
now and then.
the wire, it's just every now and then. So you can imagine how light that looked back in the 80s on an analog scope. And I'm going to
you'd
show
have
what the
hardly
tools we have.
been able to catch that at all.
Oh, but I could by staring at it. So the way I caught this in the old days is I stared at the scope until I burnt my retinas, then I would look up at a white wall, and I
you
would
see
actually
the-
point at the wall in reverse. Yes.
Yeah,
And then later I find out astronomers do something similar. When astronomers look for meteors, they actually look for black on white. The human eye is better at black on white than it is white on black. It's about the persistence and the way the nerve cells respond. So look how faint that is. I'm going to throw some digital phosphor at this and see if I can make it look better. So I'm going to go to spectral. Okay, there's temperature, and look at the blue. You can actually see it.
Yeah.
Now, if I cut
Yeah.
that wire, which is what I'm going to do for a Hackaday thing, this blue actually had more problems right around in here. But this is a late cycle for the Z80 that we let through. It got there just in time, and we say, go on through. But you see how much, if this is a 6502 here, here's the Z80. Actually, this is Z80 and 6502, and then this is just a late Z80 cycle. It's barely getting there in time, but it is getting there in time. And so let me show some of the different ways to brighten this up using digital phosphor technology here. There's spectral, where you're just
Oh,
changing it, but look at the red. Look at that. I couldn't
yeah.
see in the old days.
That's
I had to burn my
super
retinas to
clear.
see that, right?
Yeah. It's so
So I
much
can go
easier.
back to normal. And the good news is we can still see it here. Now, we're not looking at the reflection. We're still looking at a legal signal. And then I can go to inverted, where the least thing is the brightest. And look how bright it is now. Look at that. I can actually see the signal using my digital phosphor on my Tektronix scope.
And this is
So,
the equivalent of staring at the wall and closing your eyes, or staring
it
at a
is.
white wall.
Yes. Yes. So the plan is I want to cut the wire, and I'm not going to do it today. I want to do this in steps. And we should see this rise time right here get uglier out to about here.
Ooh.
And at that point, it's too close to RAS. It
Yeah.
doesn't have enough prop time and setup time. So that wire fixes a ringing static. Actually, it was a standing wave, I called it back then. Fixed a standing wave that was about 20 nanoseconds long right here.
So there's something important to learn from this, Bill, apart from just good signal integrity on a PCB. So
Right. We had no
thing-
signal integrity. Yeah. We were lucky to get it on the board.
Actually, if I look at your board design, though, even from the 80s, you had plenty of ground flood.
Look at the ground on it. Yes. Look in the
Wherever-
corners here. You can see it.
And correct me if I'm wrong. That was only a 2-layer board, and most designs back
It's
then
only
were
2-layer.
And 2
And it's
layers
got
was
DRAMs
considered
on it.
professional, right?
Yeah. There were no 4-layer boards in consumers back then. We had a 4-layer board for the Z8000, horribly expensive, just
Yeah.
as half the cost of a C128 just in the PC board back then.
Yeah, that's outrageous. So a 2-layer board was status quo and really the king, but you had ground, but you just had to fill in ground wherever there was space, right? And we didn't even, back then, we weren't thinking about return paths. We were
Right.
just thinking, well, there's going to be ringing because that's what PCBs do, but it's okay because as long as it settles before this clock edge or this edge of this event happening on this other line, we're good. And that's exactly what we're looking at here. But that actually, if you think about it, that's why a lot of designs, particularly, quick and dirty breadboarding, people are still doing that, and it still works because if you're not, this is why we talk about clock speeds. People say, "Oh, it doesn't matter. I'm not going 100 megahertz or 300 megahertz. I'm only going 2 megahertz or 10 megahertz with my design, so it doesn't matter." Well, actually, yeah. If you think about it that way, it's all about setup and hold times, and if you're below a certain sort of rate of changing things, like this RAS is actually a type of clock, if you think about it.
It is a clock. Yes, absolutely.
It's a clock for the address bus. And
For a
there's-
strobe.
and
It's a
CAS
strobe. Right.
Yeah, CAS, and those are actually in DDR2, DDR3, and DDR4, and so on. Those are actually a differential pair, and they
Right.
are treated like a clock, and they have to be length matched and everything. And the reason for that is we're now at such a high rate we're now at 800 megahertz. If we're to treat it like a clock, it's 800 megahertz, and then. So that means
it's
your
the rise
setup
time.
hold times
Yep.
are that much smaller. But it's the same principle. And so if I were designing logic using discrete logic chips to break out, let's say I had a microcontroller and I wanted to break out some IOs using 7.4 HCT 245s. I think Wes was talking about that in one of his projects.
He was talking HCTs. Yep.
That's still a decent way to do things. I like to use an SPI bus with a bunch of 7.4 HCT 595s. Because
ACTs, right?
They just hook right up to an SPI bus and I can serial stuff out to them real quick. But it'll work even if there's poor PCB design and maybe I'm only on 2 layers and don't have enough space for grounding. It'll still work if I'm keeping everything slow enough. What we have to contend with is if it's a commercial product, it's going to make noise.
Yeah.
All that ringing makes EMI. So then that's become the modern problem, right?
Right, right. And if you look at the PC board, I'll make it large here again. There are two grounds. It's not going to let me this time. But there's a ground around the edge that I used for shield ground, and then there's another ground just inside of it. And there's a shield that went over this. So this thing was noisier than heck, but I had good shield. I knew not to put current through my shield, right? And so the shield is tied to a common ground point back up near the power supply. So this area you see on the, here, I'll go point to it.
So the shield was your Faraday cage to reduce EMI.
That's right. That's right. Matter of fact, we had a cage in a cage. Hold on.
So that sounds really expensive.
If you're not Commodore, it'd be really expensive. This is the Faraday cage.
How did you guys make those things and make it?
This thing cost me less than $1. This cost me pennies.
Are you kidding?
No, because I had them made in millions. So we clamped it on, we fastened it down. Look at here, we used it as a heat sink then. And that's the actual 35-year-old bird shit, heat sink grease, on the tabs. Where's the heat problem from? The heat problem comes from the shield, right? The shield makes the heat problem, and the shield solves the heat problem. And I have people tell me, oh, you must have misused the chips if you needed a heat shield. No, they're in spec, but we made them hotter, we made them cooler, we called it a wash, with this. So we had a Faraday cage inside a Faraday cage.
But you could run them at the speed you wanted, that was the point.
Yes, so the holes. So there's holes in this. Wouldn't you think EMI would leak out of the holes? The apertures?
At millimeter wave it would.
Right. Well, I'm only worried up to 300 megahertz, FCC part 15, subpart J, right?
Yeah.
Part
and
15.
Millimeter wave, I doubt there's a lot of millimeter wave coming from those devices.
We didn't care. We weren't FCC scanned for it. We only scanned up to about 350 megahertz as part of FCC submission, subpart, the B class, which is the more stringent class.
Yeah.
So, yeah, these are 3/8 inch. My memory is these are 3/8. That was my favorite size because I knew 3/8 was a reasonable size aperture for heat and stuff, and yet didn't let through 350 megahertz. So somebody should do the calculations and check me. I was a kid. I didn't know the math behind this. I had just learned the hard way that a 3/8 inch hole didn't affect my FCC. So I knew about apertures. I would look at C apertures, like wherever a seam was. That's a big long slot, right?
Yeah.
You start seeing where metal folds against other. Yeah, it becomes energized. It receives it can even receive at one frequency and transmit at a different frequency, in my book, right? Because it just retunes the energy.
Because of different resonances, yeah.
Yes, yeah. So part of and in that band that went around the outside edge, we had experimented with spacing vias around the outside edge so that the top and bottom of that shield never got far apart. We didn't want the one side to become energized, right? But we found that we didn't need to do that. It just didn't affect us either way. So we saved the money and didn't put the vias in. So anyways, yeah, here you can see. So my goal is to I want to start the Hackaday thing before I modify a 35-year-old computer. And in theory, when I cut that trace, this red trace, when I cut the copper or the wire, you're going to see it bounce right in here.
Yeah.
It'll go up, it'll get hazy, and then it'll get clear again. And that was enough that 20% of the time the Z80 would crash. And I just love it that I could see this 35 years later and know that I wasn't crazy, right?
Yeah, that's so cool. And also that kind of level of ringing can occur too because of metastable state. So we've talked about that before. A few weeks ago we were talking about
that's right,
metastability. And you're looking at that. If you get excessive ringing because of signal integrity on the trace, it can put the signal into that zone where it's not sure, the input gate is not sure whether it's a 1 or a 0, but those gates have, particularly CMOS, have super high impedance inputs and super high gain. think of it as a ridiculously high gain amplifier. And so that ringing from the PCB trace then turns into much higher frequency ringing from the actual logic gates.
Right. And you propagate that unknown. The inside the gate, the next layer of gate starts to go, well, maybe I don't know what a 1 and a 0 is. And then it could even leave the package and get into the next guy. Yeah.
They can all start oscillating at 50 or 100 or higher megahertz, and you have an EMI nightmare. So
I knew a guy that designed with the old...
is guarding against that metastability, yeah.
I knew a guy that designed with old ECL, and he had a metastability state that he said when I single-stepped the ECL computer, and he said it was a honker. He's talking about a breadboard this big, right? He would single-step it and it worked fine. When he'd run it, it'd blow a 50-amp fuse. And he traced it to one gate, going metastable, cascading through the thing, and now all this current's flying around, and ECL is current intensive. Emitter-coupled logic is current logic, not voltage, and it would suck up the current and pop the fuse.
Craziness.
Right. Mike just said, after 35 years, you don't know if you're remembering the thing or remembering the memories of the thing. Mike heard that from, who'd you hear that from? Buzz Aldrin or somebody, I think it was. And that's so true. I have a few memories where when I touch them, I go, don't touch it too much because that's still a real one. But yes, my memories, I've told these stories so often that I'm reciting them, you know.
And you know what? I love it. It's a double entendre. You know why? Because...
Go ahead.
Because it's about persistence.
Do you know what persistence of vision, the ray tracer is? POV ray, it was called. It's the early ray tracing program, persistence of vision. So back in the 90s, I was walking remember when they used to have software stores in the mall? Remember malls? I walked by this bookcase and I stopped and I backed up and I bent down and I picked out POV Ray Tracing version 2.0 as a book. I go home, I learn to do ray tracing. I create a screensaver for the company I worked for called ADP, and it was like a marble floor with a bronze ADP rotating. Everybody loved it. Pretty soon everybody had it as a screensaver. Then they come to me and say, can you do something for the video we're shooting? Well, I meet the cinematographer and he goes, are you interested in dating this girl I know? So long story short, I date her, I marry her, and my son is born, all because I stopped and saw this persistence of vision ray tracing book on a bookcase in like 1993, and I backed up and pulled it out of the bookcase. Had I not done that, I would never have met my wife. I would never have had my son.
Dude, that is an awesome story. I love
it's like one of those moments in time. Right? It's like this junction. It's like metastability in your life that when it landed where I had a kid, you know?
Totally.
So, yeah, we collapsed the wave function. We should talk about wave functions sometime. But what I know about them, I could say in 2 minutes and be done with. Well, so, hey, you know what I'd love to do? I'd love to know what's the impedance. So this is feeding an LS257, and what we're going to find out is this reflected off of the 257. When it got there, it said there's no termination. I'm turning around, I'm going right back down the way I came. You talked to me probably at about 100 ohms. I hit the LS part and it's not 100 ohms, some portion. And there is a 22 ohm resistor in series with some of this, not all of it. What I'd be interested in doing is there a set of S parameters for an LS257? Could we determine what the input impedance is? And is the input impedance different at VN low as opposed to VN high? In other words, when the transistors turn on, does the impedance change? And I don't know the answer to that. I know what I think is the answer to that.
Yeah, the hypothesis is the impedance would be somewhat different in a high state versus a low in transistor logic because you're using current to turn on the gate.
And there's different devices with different currents which equal different effective resistances, etc.
Right. Right. And also because with logic, we're driving those gates, if not into saturation, very near to it.
Right.
So,
Right.
and I think they have, stuff in the silicon to prevent them from actually going right into saturation, because although that can be energy
That's why they're
saving,
Schottky. Yes.
it slows everything way down. So,
Right. It's
but
like overfilling a bucket with electrons. You have to drain off all the excess electrons before you can finally get to the ones that'll cause you to shift between a high and a low.
right,
When
and
it's saturated.
similar kind of things happen with MOSFETs with gate charge too. But
Yes.
but
Yes.
this is something that I still every now and then go back to and have to rewrap my head around it. But it's this notion with 5-volt logic systems, with discrete logic and the 7400s and even CMOS with the 4000 series, the input impedance was deliberately extremely high because you don't want to use energy just turning something on.
That's right. That's right.
But also, it was intentional that we were actually deliberately, and this wasn't even, I don't think this was even planned, it's just the way it kind of naturally occurred. I don't think anyone set out to say, well, we're going to invent this new thing, it's called transistor logic, and we're going to deliberately make the impedance of the traces on the board much lower than the impedance of the input impedance of the gates. No, they didn't. They just did it. They just said, we can turn transistors on and off. Let's do it. We'll hook them up with wires on a printed circuit board.
Yeah.
But later on, we've come back to realize that we actually have reflections, and we rely on them to get the voltage to go to the
its
full
final
VCC.
point. Yeah.
Because if you had an output of a gate that would signal a 0 at ground and a 1 at 5 volts, but it had a 50 ohm output impedance, and you had a 50 ohm trace and then a 50 ohm load, then the maximum voltage at the input of the load is going to be 2.5 volts.
Right.
We don't want that. That's right in the uncertainty region. We want it to go all the way up to 5. The reason it goes up to 5 and settles at 5 is because the load is at an ideally infinite impedance. So there's always an impedance mismatch, and then it's like, well, hang on a sec. That's when that changed was when ECL came along. So ECL was different and used different voltage signaling levels and used current.
Minus 5.2, yeah, things like that.
Right.
Yeah.
So that was then deliberately made, and that was done. Well, we're going to sacrifice power for speed. But now we have voltage-based. We have CMOS, but it's just super fast, and so
very low capacitance, so that so you don't need a lot of current. The capacitance doesn't absorb that current and get hot, things like that.
Yeah, but
in addition to the resistance,
we have such low output impedances from gates now, and such high input impedances to gates now, that the reflections, depending on the circuit board trace, can actually be so timed that with edge rates that they add up in such a way that the voltage goes over our power supply voltage, and it's too high. So we get overshoot, undershoot, ringing, noise.
Which overshoot and ringing count against you, as you've been saying all along here. You would think, well, once I cross 5 volts, do I care? Yeah, actually going past 5 volts on an input can make the output go unstable again. You're no longer in its zone of where it wants to be. So going below ground or above 5 volts, you have to wait till it comes back before you start your setup timing specifications.
Yep.
So ringing's bad is bottom line of that.
And
the ringing, the frequency of the ringing will tell you a lot about where the ringing's coming, but because there's a natural frequency to that, and you start to get a feel for it. When it's a real high frequency, you know it's a short trace. A longer frequency, you realize it's something else going on.
Right, exactly. Well, that's time domain reflectometry, isn't it?
It is.
You're
yeah,
measuring
it's
like
just
this spike here is a reflection from that distance, and you know that because you know the propagation delay
Right.
on printed circuit board material, and you can actually measure the time and go, that directly correlates to that distance round
Right.
trip, because the signal goes down and then reflects back, so it's
Right.
twice the distance. So
and I couldn't do the math back then, but I was like a 24-year-old neural net, literally, and so I could learn what that frequency meant in, that natural resonant frequency meant in real life. Yeah.
Actually, I love the point you just raised. A really interesting and important point too about learning is that there's more ways to learn than just reading a book and memorizing facts and learning math. All of that's really good, and it's a condensed way to learn. But don't ever neglect the intuition.
And experience, just troubleshooting experience.
Exactly. You get intuition with experience, and you don't have to know the math behind why something works or not to be able to know when there's a problem and how to fix it. I'm not discouraging people from studying. I encourage that too, but I'm just saying, don't shun.
We didn't have the internet back then, so I could only learn from books and people.
Their practical experience is not to be shunned, is all I'm saying.
Right.
Yeah.
So one of the things that made me a good engineer, it was like wax on, wax off, if you've seen the old Karate Kid movie.
Yeah.
I started as a TV repair. I fixed CB radios, TVs, and I troubleshot hundreds and then thousands of units before I was 20. So I had troubleshot so much that I learned these things, again, without sometimes, knowing that there was math behind it. I just learned these like you said, the natural frequency and stuff like that. So yeah, I attribute my wax on, wax off was being a TV repairman, at one time. And it's RF, so you're actually learning at high frequencies too, in the IF and RF segments of the TV set. So, hey, before we get much further, let's talk about Vintage Computer Federation. They go by now.
Mm-hmm. Mm-hmm.
They are having a swap meet April 24th, and I posted to.
Do you have it?
You know what?
Do you have the details on screen you can show us?
Let me post it to the chat.
So we can go and post it on YouTube as well for those who.
Yeah, I'm posting it to the YouTube chat. And let's see, am I up on Discord? So we talked about getting Jeffrey Brace to join us next week, but we don't know if we can do a three-way call. But the plan right now is to have somebody from VCF join us and talk about this. And this is in northern New Jersey or central New Jersey that this is occurring. All right, so here we go.
I'm gonna
Discord.
I'm going to put it in the announcements channel in Discord.
Okay.
Maybe you could, because YouTube wants to kibosh the link. I hate how every site does that now. They all wrap every link in their own link so they can track everything. I mean,
where'd you ask me to post it?
Oh, so there's an announcements
channel. Okay, I'll put it there. Hang on. There's that infamous short-term memory loss of mine there. Announcements, and we'll boink. Okay, it's in announcements in our Discord. Again, to get to our Discord, go to Coriolis-effect.com, and the Discord invite's there. I think I also dropped it into the chat earlier on. So yes, VCF, hopefully we'll have a guest next week. I'm not holding my breath now that I read up on Skype. We can't add him to a call. It's like we have to drop both you and me and then make a group call. So there's no way to just have somebody call in while we're already on.
We can figure it out. We have the technology.
Okay. It's only see. I these days I believe that the ability for bad programmers outweighs the ability of good hardware engineers to troubleshoot everything. Which brings me to the Coral AI thing, but I'll talk about that in a second.
Yeah.
Here's another thing. We got 10 minutes left. This is for all you. I don't want to call you hackers, engineers out there. PCBWay reached out to me, and they're having a contest with the Raspberry Pi Pico. And they asked me what would pair up good with that. I just threw it out. Hey, stick it with a Coral artificial intelligence accelerator. And he said, good, here's free credit. I'm like, well, I didn't mean me do it. I just meant it's a good idea to do that. So what I'll challenge you all with is, if you can think of something good to do with a Raspberry Pi Pico, talk about it in Discord, or email me, bheard@c128.com, HERD, and I'll send you a Pico. They're giving me like up to 4 of them, but I'm going to want to know what you're doing with it, and I'm looking for programmers too, because any good project needs hardware and programmers, and I just don't like programming anymore. So we're going Raspberry Pi Pico contest.
Yeah, we're going to follow up also on the announcements on the Discord. So if you want to come back after seeing this and get the details, we'll copy what Bill just said. We'll transcribe it and put it in the Discord.
Yes. Somebody just asked if CB radios were AM. Yes, absolutely. They were amplitude modulated radios back then. They were little 5-watt Class C little power transistors running just right into the antenna almost. It was only a coil or a cap between them.
And they gave it to the community at 27 megahertz because the FCC looked at the whole band and said, well, 27 megahertz we can't use because every ignition coil in every vehicle in the country is transmitting at 27 megahertz. And making whole lot of crap. So we'll give that band to the community unlicensed, and you can do whatever you want with it.
You know what you could hear real loud back then? Back then we still had copper spark plug wires. And they are tremendous spark gap generators. Nowadays, a spark plug wire in your car is a composite of some sort on the inside.
I've seen that. Yeah, it looked like conductive plastic or something.
Yeah, and you have to crimp it. You can't solder it, all kinds of stuff. But back in my day, you could tell a car go by and you'd hear on your radio, and you know it had copper ignition wires on it.
Yeah, my cars all have the ignition coil is a potted unit that's straight on top of a tube that plugs straight into the top of the spark plug on the top of the engine.
Right, right.
Each one has its own transformer for generating the high voltage. It's crazy.
So, hey, we got a few minutes left. Wes reminded me of a story, and if you want to hear a story, I was going to start by asking, in Australia, how's the ring voltage done on telephones? Are you familiar with? Are they common mode or are they differential? The voltage that actually makes the ringer ring on the old telephones.
They're differential. Yeah, the POTS telephone system in Australia is a 50 volt DC biased, so that there is a 0 volt line and a 50 volt line that's always at 50 volts. It can drop as low as, probably 35 or something, depending how long the wire is. But
IR drop.
But then everything is superimposed over that as a differential pair. So the analog, the voice channel, it treats it it's a roughly twisted pair for noise immunity and for reduction of crosstalk, because they have hundreds of wires all shoved together.
Right. And scientifically, there's science behind their position in that 300 pair bundle too.
Yeah, and they're all twisted and
then twisted around another twist.
A sort of random way, so that the crosstalk is spread out and even amongst all of them and minimized. But the ring is a high voltage pulse superimposed over the line in AC.
Right. So I had a story told to me by Terry Ryan, who did basic on the 128 behind me, right? And he said that, and this is back in the 70s, 80s, early 90s, before the internet, before the number of urban lefts. In other words, I believe the story I'm about to tell you. And the story was that in England, where the POTS, plain old telephone service, POTS, is done a little differently for the ring voltage. And what the woman noticed was the phone wasn't always ringing. And so she called out the repairman and said, sometimes the phone rings, but I miss calls. while the guy is there, and he literally like witnesses it, but he also hears the dogs barking out back, and he's like, starts to put two and two together as he's troubleshooting why this ring doesn't go off. What had happened in the UK, they don't do the ring voltage differentially. They do a common mode. They put the voltage between both leads and ground. So instead of having the voltage between these two, they raise these two above ground. Well, it turns out this woman had staked her dog to the ground post at the telephone pole. It's not making good ground at first, so the phone doesn't ring. It goes up to 80 volts or whatever, does this thing, but to ground. Dog does get a shock, though. He is actually, part of the conductive system. Urinates. The urine completes the circuit, and then the dog phone. So the symptom was the dog would bark every time before the phone would ring. And I actually believe that story, and because it's got facts in there, like it's a common mode ring voltage type thing. So poor dog is all I got to say.
I have to say, if it really works that way, that to me is a dumb system. But who am I to say? The great minds that came up with
who are we to think that ground is ground everywhere, right? And of course radio works that way. We talked about AM, FM radio. Even though there's an antenna on your radio, there's also a wave traveling through the earth in exact, you'd call it exact, right? The air wave and the ground wave.
Well, I'd say the ground is, the wave itself is all in the air, but the electron movement that propagates the wave is happening in both the conductor and in the ground. It happens in the conductor of the antenna and in its ground.
Right. Now, have you heard about if ground effects caused by clouds in the sky? Have you ever? Do you have any stories about that? I have one.
I don't. No, go ahead.
So, the guy Joe Mishko, who did the VAX back at Commodore, told me this story. He was working at a area that had a big data center, and they had a ground, and they were getting between corners of the building. They could get between 8 and 9 volts difference between the grounds. The AC ground had 9 volts difference sometimes. And you don't want that in a data center. And they're trying to figure out where this is coming, because it would fluctuate, it would come and go. Well, finally, they look up, and what's happening is as a cloud comes over and hits one corner of the building before it gets to the other corner, there's an electron cloud following the cloud, because I think the cloud's positive charge. And it's actually this shadow cloud in the earth following it would actually be measurable as it passed through the building.
That's intense.
So they actually these days they put ground railings around buildings for lightning, among other things.
Yeah.
But it also creates a ground bus that makes the ground be the same ground at both opposite ends of the corner of the building. That's ground
crazy.
is an opinion, people. You call it ground, I'll say that's just a current source.
And what you also want to do is, if you're pouring a massive concrete slab for a factory that's going to be a long building, it's going to be steel reinforced. So you might as well, and I think they do this in large construction, but you might as well hook a wire into that every so often and clamp a wire to your rebar before you pour the concrete into it, so that you've got that connection. You've got several connection points all along,
right?
Because that forms a really beautiful ground plane.
It forms a grid. Then at that point, yeah. And grids. We're out of time, but grids. We could talk about square terms and grids at some point. How if you have an infinite number of 200 ohm resistors in parallel, it's 0 ohms.
Where it approaches it.
Yeah.
Synthetically. So Bill, we're out of time, but we didn't get to the TPU, the tensor board you've got. Can we dive into that maybe a little bit next week? And
yes, absolutely.
I haven't done it yet, but I wanted to do it today. But maybe we'll do this maybe next week as well, as an open design review of my my smart display project. It's basically a single board computer with a TFT on one side, an FPGA, bunch of memory, and an ESP32 on the other side.
Right.
But
and we also had somebody else
wanted to do an open review with the group, so that
Right. Yeah, and I love design reviews, as we've said. Yeah.
So that's the coral It's called
That's the Coral, from Coral-AI. It's a tensor processor unit, which means I think of tensor processors as handling n-dimensional arrays, not easily, but they're set up to handle them. The problem I had with this is I follow the instructions directly. I go through all the crap of getting Python to work in a Windows environment with an MDT bash shell that finds Mendel Linux, all that, and then you run the Python script and it goes, oh, I can't bind the address, illegal function call. I'm like, guys, you're frickin' Google. You've got the instructions. I tried it on 3 computers, and you've got a bad function call in your stupid Python. I fracking hate programmers. You know, so the bottom line is I may end up doing this on a Raspberry Pi with the USB accelerator if I can't get this to behave. Now,
that's probably
I did
exactly
find
what
this.
They want you to do. They've deliberately introduced friction to get you to go a certain way.
Go the other way. And this is available as a $20 module too. So we could literally build a TPU onto a Raspberry Pi Pico, for example, you know, with a carrier board and make the smartest Raspberry Pi I've ever seen, you know, Pico, by doing that. So
that would be cool. But what kind of things do we want to learn with it? Because see, the whole thrust of what, this is just my opinion about machine learning in general. The thrust of all the machine learning hardware so far produced in the world is about, number 1, speech recognition, number 2, OCR and visual machine vision.
Right.
And everything, including these TPUs and the languages built up around it, the programming languages, they all tend to be wrapped up in listening, in basically eavesdropping activities, right?
Right,
Not
right.
Negative, but that's what it can be used for, and it can also be used to help you, can be an assistive device. But where is the machine learning for, you know, completely different things that people haven't thought of besides just replacing human eyes and ears? What can we?
That's a great question.
Project that does it for songwriting, a machine learning algorithm.
That's right. I saw that it composes songs, and you can tell it, be a little classical, put some Bach in there, and be whimsical, and it'll compose a song for you.
Yeah, which is scary. As a musician, I don't like the thought of having my creativity replaced by a machine. But the point I'm just trying to make is what could we do with this? That's not just the same old, let's learn how machine learning works.
Right, because I was going to do image recognition. This will do almost 60 frames a second of identifying a person, a bicycle, a car. You know, so you could use something like this or its smaller cousin. This really is a cool project in spite of the Python issues. You could, if you had a small robot, small whatever, drone, whatever, you could teach it to recognize objects using silicon now that we only dreamed of 10 years ago.
Well, what about teaching a robot to walk? I mean, that's like, think about the fundamental things that
you could have the sensors. You could have the pressure sensors and the level sensor. You know, I mean, physical level sensors. You could feed all that into this and tell it, go figure out how to stand upright. I'll bet you could do that.
Yeah, I think
you would need a programmer. Yeah. You would need somebody that actually knows how to, because then you have to you have to set up the teaching instances and what success is and what failure is, right? Because it needs to know, I've fallen, no, I'm upright. Yes.
Yeah, it would have to be supervised learning for some of those.
Right.
But here's what I'm coming around to. Can we feed it a bunch of printed circuit board designs and schematics and have it learn how to route?
Have it or have it learn signal integrity. That would be so hard to feed it the millions of aspects for a printed circuit board. You'd have to do an S parameter on every trace versus all the other traces.
I'm not sure, Bill. I'm not sure it's that complex compared to learning how to identify what is a human or a hand or a car. Those are very
the point with
things.
that is in a two-dimensional array, you have all the information you need to know. But for signal integrity, you have to know every trait. Well, routing, yes. I like your routing idea, but I'm talking about a reflection on A10 like I had on the 128. How would you have predicted that? without feeding it good reflections, bad reflections, and then A10 versus A9, and then the crosstalk between A10 and A9 and A8. You know, it becomes a true multi-dimensional array of
right.
As opposed to a 2D array. And sound, like teaching Alexis, that's a 1D array. That's just a straight audio.
That's right. Yeah, yeah. And we're dealing with multi-dimensional things. So, yeah, I just wonder how we would format data to get it into that, and how we could collect enough data, because you need an awfully huge data set to get good results.
That's where I'm getting at, right?
Machine learning.
Yeah.
Yeah. Wow.
All right.
That's cool, though. But I expect you to plug it in and show us what you've been doing with it.
Oh, so where I'm going with this is you can't use they run a program called MDT, which is supposed to be, I forget the name of the Linux. I should have written it down. Starts with an M. But it's supposed to be used for key exchange. Well, it doesn't run on Windows, as I mentioned. So I found it in the DHCP server. I try and SSH to it, and it goes, no, we only allow key exchanges. So my next step is to actually put an HDMI monitor on this. I've got to get a USB-C hub so I can plug in a regular USB keyboard. And so once I have a keyboard and HDMI, I'm hoping I'm pretty good at Linux. I was going to go in, modify sshd.conf and make it so that it can use passwords to log into it, and then I'll be back in business because I'll be able to SSH to it natively. And you can make it do like the recognition. You can either stream it to an HDMI output or stream it to a web port. So I am hoping to show it, but I'm going to have to cheat my ass off to do it. So, and like I said, it's at least I found it on the DHCP server. You know, when you plug in one device and you have 30 devices already plugged in. You know.
Now these Coral this
replaces a Raspberry Pi.
I was going to say it's got all that I/O and its own host, so it's not.
It's an ARM controller, ARM Cortex.
It also has a host microcontroller that gives you some interactive sort of way of working with this directly, right?
So I would have taken one of my Raspberry Pis and a USB accelerator to marry up to the thing, but they're out of stock. So I paid way more money for this. This is $179. Right now, I'm sorry I bought it, but I didn't want to wait a month for the USB thing to come back in stock. So that's plan C. If I can't get this to work, then I'm going to try a Raspberry Pi with an external accelerator, and it's supposed to work equally as good.
Yeah.
So any of you programmers want to help out with this, if you're a Python whiz, just let us know in the Discord channel. We should, final topic. Maybe we want to start, what do you think about starting groups for different discussions, like the PCBWay project, or if we do this, we'll take the conversation to the side a little bit is my thought.
Yep, we can do that. Yep, so we'll actually create channels in the Discord for those specific things. Right. And also, I just want to give a quick shout out as well about just on that topic of channels. Please, if you guys want to see us do anything in particular or talk about anything particular, there's a topics feedback channel. Definitely jump in there, give us your 2 cents. We're always open, ears wide open for suggestions. There's always a lot going on too. And Coriolis Guides is a channel. If you have a YouTube channel or have made any videos or blogs that show people how to do specific things technically, could be a hobby project you're working on, or it could just anything to do with creating electronics. It'd be great to have community involvement there, and who knows, if enough cool stuff goes in there, we can use that as a source for interesting topics to discuss in the future as well. Yeah.
Right. And remember, everybody, Raspberry Pi Pico, if that sounds interesting to you. It doesn't to me, but I'm hoping with all this young enthusiasm, we can find something interesting to work on, you know?
Yeah, totally.
So, totally. All right. Well, hey, my friend, good speaking with you again. Glad we got things working. Like I said, I had a camera fail at the last minute. Didn't stop me this time. And lots of good things here. And we didn't even get to everything on the list.
Yep, so there's always more for next week.
Yep, catch us in Discord. It's been real active lately. We do hope to see everybody there. And till next week, I'm Bill Hurd, and we got Ben Jordan. And good seeing you again.